A big thank you to Juan for doing the second episode of the Space Engineering Podcast with me. In this one, we get into his time at JPL, so he spent over 7 years there, and then why he decided to start his own company called Nabla Zero Labs, which is a company that I work for, and what we're doing at Nabla Zero Labs for the Artemis missions, which includes trajectory optimization, navigation, and scheduling. And then we get a bit into the math of the Earth-Moon trajectories, which in orbital mechanics is a three-body problem. So we get into how it is mathematically defined as a chaotic problem, and we get a little bit into Lagrange points as well. We then get into differential equations and ordinary differential equation solvers, so basically how to formulate the differential equations that go into simulating a spacecraft trajectory, and then the solvers that you use to actually solve these differential equations, including the Runge-Kutta methods and atom solvers. We then get into interplanetary trajectory design. So basically, if you want to go from Earth to Jupiter, you have to do a bunch of design in order to figure out which planets you want to fly by in order to gain heliocentric energy. So then we go into that, the infinity and sphere of influence when doing this type of analysis. We also get a little bit into floating point numbers, numerical considerations. After that, we get into outer planet tour design. So basically his work on Cassini and Europa Clipper. So basically the mission design for Europa Clipper actually orbits Jupiter. It doesn't orbit the moon Europa, but then how to use these orbits and use the flybys of Europa to get global coverage of the moon. It's very interesting, and I learned a lot basically listening to him talk about kind of the flyby design that goes into that part of mission design. And then there was this one time when Juan kind of almost erased Cassini's navigation solutions, so it's a very interesting story. And then after that, we get into deep space orbit determination, so basically how the deep space network works, optimal navigation, and then optical navigation, and then relativity and aberration corrections when doing deep space orbit determination. We get a little bit into inertial reference frames, so basically how to define the ICRF inertial reference frame using quasars. And then towards the end, we get a little bit more into software engineering, so how to use the NASA SPICE software and kernels, C, C++, and Fortran, and then operating systems like Unix, OS X, and Windows. So this podcast is available on YouTube, Spotify, Google Podcasts, and SimpleCast, so wherever you like to listen to your podcasts. And let me know in the YouTube comments if you have any questions or comments about the podcast. And without any further ado, here is the second episode of the Space Engineering Podcast. The first question I have is that you were at JPL for roughly 7 years, and you're working on super cool missions like the Cassini and Europa Clipper, and you're doing really cool stuff as far as doing mission design for those missions. So can you talk a little bit about why you decided to take that risk and go out on your own and start Nabla Zero Labs?
Yeah, absolutely. So first of all, I love JPL. I always did ever since I was a child, and I think I always will. So there's absolutely nothing at all to do with JPL. Yes, the first thing I did, so I finished my PhD in Carnegie Melon in 2007. Then I wanted to go to JPL immediately, but I couldn't because I was not a permanent resident at the time. I'm a citizen, well, I was a citizen of Mexico, and there was an issue going to JPL right off the bat. So I worked for 2 years as a business consultant. I worked for McKinsey, and I enjoyed that a lot. That finished. I came to JPL 2009, worked there until 2016. The first half, approximately, of my time there was working on mission operations for Cassini. So I designed the maneuvers that go into Cassini. And that was amazing because seeing your work actually go to space and seeing a maneuver executed by a spacecraft that was several billions of dollars just all the way around on Saturn, that was super exciting. But after a while, it becomes a little bit routine, not because there's anything routine about exploring the solar system, but because your role as a maneuver analyst or as a mission designer for a flagship mission that is already flying is heavily reduced. Most of the stuff that can be optimized has already been optimized, and there's not a lot of room for experimentation. Essentially, once it works, you just let it be, and you don't want to rattle the cage in a super expensive mission that took decades putting into another planet. So at some point, I believed that I had gained the experience that I wanted to get from actually operating a deep space mission. And then I went on to mission design. I was designing Europa Clipper. It was amazing. That was a completely different side of the coin, where everything is on the table, where you can work with your maneuvers, with your mathematics, with your computers, design new mission concepts, and everything is allowed. And that was also wonderful. And I was very happy like that. But there were two things that happened. The first one was realizing I finished my first end-to-end trajectory for Europa Clipper around 2014. And for that mission that I had designed, for that one trajectory that I had designed, I forget now, but I think the launch time was like 2024 or 2025, something like that. And then it would get to Jupiter in 2030. That was around the time frame. And I was like, I don't know, 38 years old at the time. And somehow it kind of made me anxious that the work that I was doing then, I wouldn't see it yield fruit until I was like 50 something. That was one thing that it kind of freaked me out. That I was very young, but not that young anymore. I was, bordering 40, and it's still feel energetic and everything, but you're definitely not a kid. The second thing is that at that time, everything that was promising technology since the 2010s actually became a reality. Cloud computing, the blockchain, the massive adoption of high performance computing across the board, automation, machine learning. So it seems that engineering was amazing and people were doing wonderful things all over the place. And I kind of said, okay, I'm an engineer. I think I know a few of these things. I want to modernize certain aspects of space. I love space, and I'm going to give it a shot. So I did. For some reason, I thought that if I didn't do it before I was 40, I would never do it.
So then can you go a little bit into detail of the work that we're doing at Nabla Zero Labs as far as the Artemis missions?
Yes. We are supporting three main areas. The first one is in the numerical methods and algorithms for trajectory optimization. We are developing a software suite that we already gave it a name. It's called MAD, the Moon Ascent and Descent Tool. And the purpose of that one is to enable a very accurate, optimal trajectory design for the descent on the moon and the ascent from the moon. The reason why we need a special tool to do it, as opposed to using some commercial off-the-shelf tools that are available, is because every little part of the trajectory is subject to different constraints. These constraints are expressed in many different ways. Some of them can be rates of change of certain parameters. Others can be orientations. Others can be the rate of the change of the orientations. And other ones have to do more like with the humans. Like, for example, that the human needs to be able to see the ground as they are landing. And others that have to do with targeting the Orion, the main spacecraft as we take off. So this is a complicated mathematical problem. And the tools that exist can target a few of these variables, but not all of them, unless you do some workarounds, which is one problem. And the other problem is that it's slow. And because we have different standards for reliability and security, etc., we want this tool to be able to perform massive number of simulations to make sure that we cover all the space and do it very rapidly. So that's one area of support. Another area of support is with the development of their entire tool chain to perform mission analysis and spacecraft operations. So we, as you know, we know well how to use established tools like Monty, for example, for navigation and mission design. And the national team that we support needs to get up to speed very quickly. They do not have time to experiment or to reinvent the wheel. So essentially, they need something that is proven. They maybe need to look at a couple of options, but they need to take quick decisions and move fast. So that's our secondary of support, that we establish a set of analytical pipelines for them to evaluate and just quickly tweak to serve their needs and just have their team up to speed in a minimal amount of time. And the third one, which we haven't started yet, but we are going to get there hopefully, is in everything that has to do with planning and scheduling. When everything gets married together, the different phases of the mission with the schedule of the humans, with the schedule of the antennas, with the schedule of the maneuvers, you're going to end up with this massively complicated scheduling problem where everything has to fit in its time slot. It cannot step on anything else, and it has implications that fall like dominoes. So we're going to provide, we have designed in the past some tools and some techniques to manage these very complex scheduling problems, and we hope to provide it to them. So those are the three. In general, is astrodynamics, high performance computing, navigation, and analytical support. That's what we've been doing for over a year now, and we hope to continue supporting throughout the design of the mission and on to launch and operations.
The question that I want to get to is kind of the differences in mission design between Apollo and Artemis, how they both use kind of the Earth-Moon system as a three-body problem, but in very different ways. So first, before we get to that, can you talk about the circular restricted three-body problem and how it's useful to analyzing trajectories in the Earth-Moon system?
Absolutely. So I guess to get us started, that we have to first start with the two-body problem. So the problem is most simple ideal thing with no volume, where all the mass is concentrated at that infinitesimal point. That is perfect. Namely, it is homogeneous, and it has a potential that pulls another mass with a certain force in a manner that is proportional to the product of those masses and inversely proportional to the square of their distance. So that's a very simple problem to understand. When that is the case, the motion of a spacecraft or the motion of anything in that system describes a conic section. Obviously, a circle, an ellipse, parabola, hyperbola. All these are the ways that you describe the motion in a two-body system, a very massive one, another one of a small mass that can be considered negligible only under the influence of gravity. So if you know conic sections, you can describe the motion, and there's actually some analytical expressions to study the two-body system, the most famous one being Kepler's equation. The problem is when you throw in another mass that is non-negligible. So now you have three masses or three bodies. You have one of them which tends to be more massive than the other. It doesn't matter really. It's just in practice, it tends to be one much more massive than the other. But then that other one is significantly massive, and both of them are overwhelmingly more massive than the spacecraft or the asteroid or the particle. And that's why it's called the three-body system. So now in this case, you have the 2-point masses, the third mass that is very small, and the motion in that system no longer follows a conic section. It's no longer an ellipse, it's no longer a parabola, no longer a hyperbola. Actually, its movement is chaotic from the Henri Poincaré perspective, in the sense that the initial conditions, it's a deterministic system, so there's no randomness there, but chaotic in the sense that a very slight perturbation in the initial conditions will lead to wildly different trajectories as the time moves on. And it is actually very difficult to predict where the system is going to be at a certain time in the future a priori. You can obviously simulate it and see where it's going to be, but a priori, you cannot really tell where it's going to end necessarily. Whereas in the two-body problem, everything is constant except for the true anomaly, except for your place in an orbit. Everything else is constant. Your semi-major axis is constant, eccentricity, inclination, right ascension, argument of preapsis, they never change. And you just move around that circle. And you know that in a bazillion years, you'll still be there. In practice, that's not the case, because in practice, the two-body problem doesn't exist. But theoretically, that's what happens. But in the three-body problem, even very simple initial conditions just yield extremely weird trajectories. So the Earth and the Moon are orbiting their common barycenter. And when you model the gravitational potential in that system, and we're not even bringing the sun yet, which also matters, which is called the four-body problem. But when you just analyze the trajectories in that system defined by the common rotation of the Earth and the Moon about their common barycenter and the spacecraft in that space, you end up with these levels of energy. This is called the Jacobi constant. It's an energy-like term. that defines certain regions that are accessible for the spacecraft and inaccessible to the spacecraft, depending on the initial velocity and the position where you were. And this can define some sort of gateways or pipes where you can actually find the spacecraft. You can never tell precisely where you are, but you can tell, I'm going to be within this overall region over here. And so that's one point. And another point is that you have 5 points where the gravity kind of cancels each other out. One of the most obvious one is between the Earth and the Moon. There's a point in the line that joins them where the gravitational of the Earth is exactly the same as the gravitational pull of the Moon. So in that point, in a rotating reference frame, you would have no motion. You would be always steady. There is another one on the opposite side, also along that line. There is another one in the opposite side of, say, the Earth in this case. And then there are 2 above and below that define this equilateral triangle. So those 5 points are called the Lagrange points. And these are where the potential goes to 0. Well, not the potential goes to 0. Well, the forces due to the potential are equal. And you can have a spacecraft that appears to be frozen in place in this rotating coordinate frame. So when you bring all, you can be periodic orbits, and you bring into place the energy levels as dictated by the Jacobi constant and the common rotation of the 3 system, you can end up with these very cleverly designed trajectories that use all of these phenomena to their advantages, to have trajectories that are relatively cheap energetically to get to. They remain relatively constant in a place, and they are relatively cheap energetically to get out of. So you can go from Earth to the orbits, stay kind of there, then go to the Moon, then leave the Moon, come back, and go back. So they have this, they have called it the interplanetary superhighway in other contexts, but it's similar to what we're doing here. And yeah, so the 3-body problem, it's a fascinating thing. Actually, the chaos theory was discovered through the 3-body problem. It was, again, Poincaré who worked a lot on it. And it's an inexhaustive source of complexity and beauty. It's very, very nice.
So a bit of a math question. So the fact that this system is chaotic once you add more than 2 bodies. So can you go over a little bit about how the 2 bodies or 3 bodies plus that problem is proven to have no analytical solution? So again, a bit of a math question, but can you go a little bit about how you would go about proving that a problem has no solution?
Yeah, so it's certainly a very difficult question. So the 3-body problem, as modeled in the rotating coordinate frame, where if you see it in an illustration, you would see a line, you would see a point, then a line, then another point, and so it would be for example, the Earth and the Moon, and they would never move. And it's because they do not move, the coordinate system itself rotates. When you model it like that, and you write the integrals, the differential equations that describe the motion, and then you want to take the integrals, you end up with a non-integrable system. So the integrals, the differential equations, are known not to have an analytic solution. Though they do admit a constant, which is a Jacobi constant. That doesn't mean that you could not find another formulation that could admit a solution. So it is not necessarily proven that you cannot possibly have an analytical expression to express the motion of 3 bodies. It's just entirely unlikely, because to do, they need to find how to define the equations of motion, the differential equations, so that they would admit an integral. And how something admits or doesn't admit an integral is just a matter of the literal formula that expresses the differential equation. For instance, we know that if you have a linear time invariant differential equation, given some properties of the matrices, you know that they have a solution. It's a known fact, and you can actually derive it, right? And there's other integrals that you know they have no solution, no analytical solution. Doesn't mean that you cannot solve them. It just means that you cannot have an expression that expressly given an input returns you an output. You can do the numerical methods and all, but you will never find an algebraic expression that will give you the solution. And statistics has a bunch of these examples to evaluate the error function or something like that, you from tables or do something like that, right? So the three-body problem, as expressed, has no known analytical solution, nor it is likely that it will ever have it. But if you were to express it differently, you could find other integrals. And to solve it, you don't need to find all of the integrals. You could find 1 or 2 or 3 or 4 or 5. Ideally, you would find all of them, the 6, to find the 6 constant motion. But that's what is meant, but it doesn't have an analytical solution. But again, not to be confused with it cannot be solved. We can obviously solve it and solve it very well. It's just that everything we do is numerical.
Mm-hmm. Okay, so then why don't we get into the numerical part of things? So basically we have just some equations of motion that bottle the gravitational forces and I think we can stick to the Earth-Moon system for now. So we have the equations that we need where we have a central body, say the Earth, as you're going to the moon, and then you have a perturbing body that say is the gravity of the moon. And from this, we get differential equations. So I guess first to start off, fundamentally, can you explain kind of what a differential equation is and why they're so important and why we kind of use them so much in astrodynamics?
Absolutely. They are one of the single most important invention of the human mind. A differential expression with a left-hand side, a right-hand side, and an equal in between. So it's a relationship between two entities, where some of those entities are derivatives. So normally in an equation, just a regular old equation, you have some algebraic variables. So if you want to know the total that you're going to pay for, say, a certain number of items, so the total equals the number of items times the unit price per item. So that would be a very simple algebraic equation where each one of the variables, total money, number of items, unit cost per item, would be just a scalar variable, and that's it. So you substitute, multiply, you get your total. That's simple. Now imagine that instead of not knowing what your total is, what you are trying to find is how certain thing changes in time. So you are no longer solving for a scalar itself. You're solving for the rate of change of an scalar relative to something else. For example, the rate of change of position with respect to time, i.e. the velocity. You could be solving for that. The rate of change of velocity with respect to time, i.e. the acceleration, you could be solving for that. And the reason why they are so important is because when you write the laws of nature, they normally express forces. When you have the gravity, so I mean, we cannot enter too much into Einstein and stuff like that. Mm-hmm. So according to Newton, gravity is a force. According to Einstein, it isn't. According to Einstein, it's but again, that's a complete separate topic. So let's assume that a gravity is a force. So then the only thing you know is a force. The only thing you can measure is that force, and the only thing you can express is a force. But a force, as per Newton's second law, equals mass times acceleration. So if you know the force and you know the mass, then you know the acceleration. But the problem is the acceleration is a derivative. It's actually a second derivative. The acceleration is the second derivative of the position. So if you know the force and you know the mass and you know the acceleration, it still doesn't help you, because what you want to know is the trajectory of a particle. You do not want to know the acceleration put on that particle. You don't want to know the force put on the particle. I mean, sure, you want for other reasons, but what you're interested in is its position. And the only thing you have is the acceleration. So you have to take the first integral of that acceleration and you will get a velocity. And then you have to take another integral and you will get the position. And that is why differential equations are so important, because normally any conservation principle in nature, conservation of momentum, conservation of mass, conservation of force, well, the equilibrium of force, etc., is expressed as a rate of change of something else. You can never just write, I know where my particle is going to be. You can never do that. You can only know, I know what forces my particle is going to be subject to. I know how much mass is coming in and coming out of the system per unit of time. And everything, you have these ratios of this thing relative to another, this thing relative to another. And when you try to solve them, and when you pose the equations, you inevitably end up with derivatives. And the techniques to solve an equation that have derivative either on the left-hand side or the right-hand side, obviously you can just swap them. That is when those are called differential equations. If it's just a regular derivative, these are called ordinary differential equations. If it were a partial derivative, it is called partial differential equations, when a property changes across two or more independent axes. And you can have linear and nonlinear and first order or second order or third order, depending on the highest derivative that you take. And in the case of the moon and the rocket science in general, everything that we know is the forces acting on the vehicle. So we know the force due to gravity, the force due to the engine thrust, the force due to the irregularities in the shape of another object, the forces due to solar radiation pressure, etc., etc. You of differential equations that then you need to solve. Impossible to solve them numerically. Analytically in practice. So you solve them with numerical methods.
Right. So anything past a two-body problem, we kind of have to use numerical methods in order to solve them. So I also want to get into then numerical solvers, because there's a bunch of different ones out there. So can we start with basically how to solve differential equations using computers? Can we start with kind of some fundamental differences between, say, a Runge-Kutta method of solving differential equations versus an Adams method?
Yeah. So the most important thing to understand is that all of the numerical methods are for solving ordinary differential equations are all of kind of doing the same thing. What everyone knows is if you take an integral of something in school, everyone knows that is the area under the curve. That's what is familiar to most people who have taken high school calculus. And most people know that if you had just your x and your y axis and you paint some arbitrary curve somewhere in between x0 and x1, that if you wanted to calculate the area under that curve, there's many ways you could do it. And one of them is to make a small rectangles that go from the origin and touch on the curve, and then you make the rectangle a little bit small, and then you just make a bunch of little rectangles that you know the area of each one of them. They will all have potentially different height, but you can make them so that they have the same base width. So then you just multiply the base times the height. For one tiny rectangle, you get a little bit of the area, you get the other one, and then you just add it all up, and you could get the area under that curve. So that would be the integral. And then as you start playing with that idea on paper, anyone who's a little bit clever will start saying, okay, instead of a rectangle, I'm going to use some sort of irregular trapeze. I'm going to start at the base, touch one point of the curve, then I'm going to trace a line to the other point of the curve, even if it's not quite flat, even if it's a little bit slanted, and then I'm going to go down to the origin. So they would have like these little trapeze-looking things, and they would be more clever. And then other people would say, okay, but I want to use very narrow rectangles when I'm in a very fast varying part of the function, and a very broad rectangle when I'm in this very quiet part of the function. And then some people would say, instead of using rectangles, use a quadratic polynomial or a cubic polynomial to fit the function in that area. And people could start throwing a bunch of ideas on how to make this physical process of measuring the area under a curve more accurate using less work. So people would say, I want it to be as accurate as possible, doing as little work as possible. So that is the only thing that all the numerical solvers for ordinary differential we're doing. That's the only, and it sometimes surprises people, but that's what they do. When you have a Runge-Kutta method, what you have is a polynomial approximation to a function given by a certain number of function evaluations. Sometimes you evaluate it once, in which case you would call it Euler's method. You just say, I'm here, then just give one step forward, and then tell me, and this literally just the rectangle that I spoke about, it just makes that, and it just adds it all up. Then you can have a second order method that will evaluate it at 2 points. And then whether it's implicit or explicit, it has to do with whether the point that you're trying to know it in advance or not, or whether it's an implicit equation. And then you can say, then now use a cubic polynomial, use a fourth order polynomial, and so on. So when you have, I have an RK4 method, for example, it's a Runge-Kutta method that uses these 4 function evaluations to have this cubic polynomial pass and evaluate the things. Most of them, when they are expressed like that, without any more information, you have to assume that they are fixed steps that every time that, but obviously you don't want that. You want something that adapts itself. So you end up with things like the most famous of them all, which is the RK45, which is called RK45 in MATLAB, but it was is the Runge-Kutta 4th and 5th order. The way it does it is it solves it in 4th order with one width of that rectangle, with one step size. Then it solves it in 5th order, and then it compares the two. If they are very similar, it takes a longer step because, like, okay, I'm good. My 4th order approximation and my 5th order approximation are the same. So I can take a longer step, therefore getting to the end faster. Or the opposite can happen. It does a 4th order step, then it does a 5th order step, and it sees that they are different, that the solution is different. It's like, oops, okay, I gotta go back and make my step smaller. These are called adaptive step size. And the difference between Runge-Kutta method, which is not a method, it's a family of methods. Again, there's so many that I could not even talk about. What changes the order of them, which is kind of the polynomial to create this little approximation. And the Adams method is that the Adams methods are based in this linear combination of approximations. So the Adams method is kind of, it has a line, and then it has also like a quadratic, and then it has like a cubic, and it linearly combines the solutions to get to the same approximation. So the way in which that internal approximation is made on the one hand, and on the other hand, the strategy to adapt the step size is what makes them different. But again, underneath, they are all exactly the same idea. Try to take the most accurate area under a curve, quote unquote, by using the fewest number of steps.
So can you talk
to
about
reduce computation time.
So can you talk about kind of why, say, for orbital mechanics, it's beneficial to use the Adams method over a Runge-Kutta method?
Yeah, I would say it's just experience. You've heard about DIVA, the propagator written by Fred Krug, JPL 45 years ago. And they have, for the problem of the motion in orbital mechanics, where you have point mass subject to increasing collection of forces in extreme scale, like you can have something that departs from Earth but then goes to Neptune. So you end up with in the order of 1 astronomical unit to the order of 30 astronomical units. And you need to find the vents, and you need to propagate many forces. For that, Fred really tuned the Adams method and proved that they were more reliable than the Runge-Kuttas available at the time. And this is very important, at the time when Fred Krug wrote DIVA. And again, DIVA has been used to fly many $1 billion worth of spacecraft have been flown with that software. And it's now retired. JPL, as you know, rewrote DIVA in C++, and it's just called Adams propagator because it uses an Adams method. Or linear multi-step method is also what it's called. But it's the same thing. So we have just seen in practice that these the properties of the Adams methods, of the linear multi-step methods, for very very broad scale of numbers, again, from very tiny things, Earth, Moon, to the scale of the solar system, where you have a lot of forces, and the speed with which the dynamics vary are better than the Runge-Kutta. So I just want to be specific. There's nothing intrinsically better of Adams versus Runge-Kutta in general. Like there's no one could say Adams methods are better than Runge-Kutta methods. That cannot be said at all. Because for every example that you give me of one, I could give you an example of the other. It's just that in orbital mechanics, for the kind of work we do, it has been observed that Adams is more reliable. It could also be that we have a little bit of a bias, and we just have never had a Runge-Kutta that is as fully featured as an Adams method. Now, there's other things that have to do with stability of a numerical method, that has to do with whether it's good for stiff systems or it isn't. There's obviously people who dedicate their entire lives to study numerical integrators. So we cannot get into all of that. But we have observed that Adams is better for our kind of problems. And there's nothing keeping us from investigating high order Runge-Kutta methods.
Mm-hmm. Okay. So I want to move a little bit into more interplanetary mission design. And one thing that I'm really curious about is the fact that when the mission designers go about designing, say, a mission to Jupiter or a mission to Neptune or Pluto, is that they do a bunch of flybys of the inner planets and other planets. So I'm kind of wondering how that process goes of going through design, because I feel like there's so much freedom and the problem isn't very restricted, because I feel like you can do Earth, Moon, Venus, Mars, flybys, and you can just do a bunch of that. So I'm wondering, just how that process goes of actually picking these flybys.
Sorry, could not hear the last part. You are wondering if you can pick what?
Oh, just the process of how to pick these flybys, just because there's so much freedom to pick just whatever, order of flybys, like Earth, Moon, Earth, Venus, Mars, all that.
Yeah. So there's two answers. The first answer is there's no way to pick them. You just have to try them all, which is the bad answer. The good answer is that we have some idea. So the first one, you have probably heard that Tisserand, an old astronomer of the, oh God, I forgot, I think it was the 17th century. Anyway, this person of last name Tisserand invented a criteria for when a comet flies by Jupiter, it sometimes explodes. And then you had one comet, and then it passes by Jupiter, it explodes, and there's several pieces of the comet. So at some point, they didn't know which piece was from what comet. And this guy, Tisserand, developed a criteria that said, okay, everything changes after the flyby and the subsequent explosion, but this one parameter approximately doesn't. And he invented this criterion that allowed you to distinguish one thing before and after a flyby. So we use something similar. You can tell a priori what kind of change in your orbit you can expect from a flyby with each one of the planets or with any massive body. You know what is the mass of the body, depending on the incoming hyperbolic velocity that you have with respect to the body and the altitude that you fly by it. You know how much it would rotate your velocity vector relative to the sun or relative to the center of the trajectory that you are investigating. And you can bring these arguments into some sort of energy argument and finally develop something that is called the Tisserand parameter, which is inspired by this guy Tisserand. So you create these plots that tell you, okay, if I was at Earth with a VMT of so-and-so, say 9 kilometers per second, and I made a flyby, I could energetically reach, for example, Venus. And if I did, I could reach it approximately with this so-and-so hyperbolic velocity. And if I did, then I could reach, say, Jupiter, or I could reach Earth back again, or I could then orbit once and then reach Venus back again. And so we do have some guideline on how to look. So you know that you are not in one flyby going to reach Uranus. You know that because there's energetically not possible. Your time of flight is not sufficient. There's not enough energy in your orbit to have an apoapse that will intersect the orbit of the planet that you're trying to reach. So when you have that Tisserand criterion, your energy arguments, your charts that allow you to see flying by where, approximately where could it take you, then you have to deal with the second problem, which is the phasing. Namely, it is energetically possible to reach, say, Uranus with a flyby of Jupiter powered by Earth. It's energetically possible. We know that. But that doesn't mean that Jupiter is going to be in the good location. Mm-hmm. So then you have to find it. And unfortunately, I mean, there are some approximations. You can assume that all the planets move in a circular orbit, which is not too bad of an approximation, that they are coplanar to the ecliptic, which they are not. You and say, okay, I'm going to start with circles. I'm going to get some sort of timing. Then I'm going to, from the circle solution that is coplanar, I'm going to add some ellipticity. I'm going to add some out of plane full ephemeris. What we have done at Nabla Zero Labs, to search it in a full ephemeris. So it's not high fidelity, but it's full ephemeris very fast. And honestly, in my experience, I very quickly use a Tisserand-like criterion to discard what I cannot search. I say, okay, I'm not going to consider, for example, Mars. I'm not going to consider more than 2 Venus flybys, and I'm not going to consider Saturn. Everything else is on the table. And then I just set up my time of flight bounds. I say, I want to depart from Earth with the launch vehicle. I know what Neptune within 20 years. And then I just filter what I'm not going to do and just start a very coarse search throughout the rest of the domain. I leave it running for 3 days with several computers and just to get an initial peek at what's out there. And then once you have this very broad search after some high performance computing, then you start zooming in some regions and say, oh, look, my Earth, Venus, Earth, Jupiter, Neptune are looking good for the 2040 decade. And then you start fine tuning it. You say, okay, oh, you see the flyby, it starts getting out of phase here, it starts getting in phase here, and then you start pinning it down. But at the end of the day, you just have to run a bunch of studies. Again, you can study some energy arguments to know what not to do, but it's artisanal and computationally a very expensive process.
Okay, so once you have kind of some candidates, say you're doing a mission to Neptune and you have some candidates of trajectories that do a certain amount of flybys, so how do you go about then refining these trajectories to make them higher fidelity? So as far as you know what maneuvers you're going to do, as far as propagation, do you use a patch conics way of propagating methods? So yeah, how do you start refining these trajectories once you found that these are feasible and I want to look more into these?
Definitely. You always start with the best friend of the mission designer, which is the Lambert solver. The orbital boundary value problem is the name of the problem that connects 2 points in a space with a single point mass. So it's a two-body problem solver. It connects 2 points in a space in a pre-specified time of flight. Given the 2 positions, it gives you the 2 velocities that will make that conic expand the 2 positions in a prescribed amount of time. So you get that solution. If you have to make a flyby, then what you need to do is, okay, I go from, say, Earth to Jupiter. I solve a Lambert arc. I get the velocity at Jupiter when I came into Jupiter. And then say you want to go Jupiter, Neptune. So then you solve a Lambert from Jupiter to Neptune, and that will have, so you have now an incoming V infinity at Jupiter, and then outgoing V infinity from Jupiter. And you have to, because energy is conserved during a flyby, relative flyby body, So you know that the energy of an orbit, so energy is the square of the velocity divided by 2 minus gravitational parameter divided by the distance. And because the velocity is conserved there, the only thing that can happen with a v infinity vector is that it can rotate, but it cannot change its magnitude. So you need to have the magnitude of the incoming v infinity be the same as the magnitude of the outgoing v infinity. And then you have to evaluate the angle by which you have to rotate the first one to get the second one. And that angle has to be compatible with the flyby altitude. There's another formula that allows you to compute the flyby altitude given an inbound and outbound v infinity vector. I forget it, but it's again like outbound v infinity minus inbound v infinity. The magnitude of that equals twice v infinity divided by 1 plus twice v infinity divided by nu, I think, something like that. So with that, you get the minimum flyby. And then you are like, okay, I got my Earth to Jupiter. It has a given v infinity vector. I got a Jupiter to Neptune. It has another v infinity vector. The magnitude of this one is the same as the magnitude of that one. And the angle between them is within the altitude that I'm willing to go. Say is greater than 200-kilometer altitude. So then you get this parameter. So that is called the patch conic approximation. And now when you have those two, you can say, okay, now I want to solve it in full fidelity. So for the flyby, given the inbound and outbound v infinity, you can calculate an approximate, what we call full fidelity state relative to the flyby body. You normally calculate the b-plane parameters, but you can calculate the position and the velocity of the spacecraft relative to the flyby body, and you convert that state onto the b-plane target. And then you now have an initial condition, a b-plane target, and a final condition. And you use that as the initial guess, as the initial iterate for a full fidelity, multiple shooting, collocation, what have you. But that is normally the process. Lambert, C3 matching or V infinity matching, approximating the states, getting the B-plane targets, and passing those on to the full fidelity solver that uses full ephemeris. Calculating the launch window is a little bit different because you only have an outbound V infinity vector. And that one, you just have to start in a circular orbit around Earth and pick a point in that orbit that will result in the same outbound V infinity vector. So you get the right ascension, declination, and magnitude of the outbound asymptote, and you just find the circle at which you applying a delta V, you will get that outgoing hyperbola, and then that's how you go, and then you just start coming into the next one with another V plane, and off you go. It's easier said than done, though.
Yeah. So can you talk a little bit about as far as the patch conic sense, so doing center switching and sphere of influence? So say as you're coming into Jupiter, at what point do you want to say that I'm no longer in an elliptical heliocentric orbit, I am now in a hyperbolic Jupiter orbit, and then once you come out, I'm no longer in this hyperbolic Jupiter orbit, I'm now back again into a heliocentric elliptical orbit?
Yeah, normally when you, the answer is both simple as complex. When you want to consider Jupiter as a flyby, in the case of Jupiter in particular, you would always do it when you are within its actual sphere of influence, which you can calculate. In my case, to me, Jupiter is a 2 million kilometer kind of deal. If you are 3 million kilometers from Jupiter, I normally do not enter the sphere of influence. I normally don't consider it as an individual point mass subject to the little moons orbiting. I just consider it like a barycenter with all the mass aggregated at its center at 3 million kilometers, just as a rule of thumb. But if I'm considering as a flyby, it's normally because I'm closer to it, like say 2 million kilometers and closer. Then it is just, I put the pointer, and when I get to that 2.5 million kilometer distance, then I trigger the center switching. and precisely what you said happens. You are heliocentric, elliptical, not necessarily elliptical. You can have a non-elliptical, like New Horizons, for example. It had a non-elliptical orbit relative to the sun. It was like screeching when the spacecraft took off. Heliocentric, the B plane, which are approximately linear relative to the velocity at the beginning. That's why we use them, because they are not as wildly varying as the norm. If you just compute the distance to Jupiter, that's obviously a quadratic, because you have a vector, another vector, you subtract them, and you take the norm, which is a square root. So it's a square and then a square root of the square. So that has, unfortunately, it's very numerically complex, whereas the B plane, it's almost linear. That's why it was designed like that, because it uses hyperbolas. So you only, when you consider the body as a flyby, you do the center switching. When you consider it as a disturbance, you do the center switching. And if you define your spheres of influence appropriately, namely, I should really learn that formula. I don't know why I never learned it. There's a formula that to calculate the sphere of influence of a body relative to another. And you just is just to derive it, is what is the radius that, given the mass of this body, what is the radius at which the force that I'm feeling is the same as that other body in another sphere. So if one body is very big, then the sphere is big. And then if it has another tiny body, then this one has a sphere. And if you get very close to it, at some point, the force is going to be the same. So that radius is the sphere of influence. So you just compute the actual sphere of influence for each one of the planets. Normally, it goes well. Unless you're in the Earth-Moon. In the Earth-Moon, you often always want to use both independently. Both the Earth and the Moon as independent bodies. Never collapse them onto a common barycenter.
Then one thing, going off of kind of like the numerical errors you can get from a norm, I remember that there's some numerical problems that come up when you have, say, a very large distance, say from the Earth to Jupiter as a spacecraft is flying by, versus the distance from, say, the spacecraft to Jupiter. So like it's a very large number where it's like, I don't know, or a few astronomical units versus the distance of the spacecraft to Jupiter. I remember you talking about at one point how there's numerical problems with the fact that you're dealing with such large numbers.
When you there wouldn't be any issue if the computers had infinite precision, but they don't. They have, if you use a double precision number in the computer that has 64 bits of precision, so 8 bytes, and you can only represent so much, right? So you have approximately 16 digits of precision in a regular double precision number, plus the exponent. So the problem is that it truncates. So when you subtract two very similar numbers using floating point, not integers. If you subtract two integers, you're fine. But then an integer cannot represent everything, right? Unless everything was discrete. So a 32-bit integer, like a regular int, can represent 2 to the 32, which is like 4 billion. But we obviously have more than 4 billion millimeters in the solar system. So we could not use integers to represent the, say, millimeters in the solar system. Neither could we use, say, 64-bit int to represent micrometers and say, okay, I'll just use everything discrete so that I do not run into numerical issues. We cannot do that for there's several reasons. First, because they don't fit, and second, because doing integer manipulation is complex when you do transcendental functions like sine and cosine. But anyway, going back to floating point, because you cannot represent the distances, when you have two double precision numbers and subtract them, and they were very similar, they lose, like, depending on how you do it, like half of their precision. So when you are doing gravity calculations and you have the bodies considered independently, so you have Jupiter and Ganymede relative to the sun. So all two vectors are almost identical. They look very similar there. But at the scale of the solar system, relative to the sun, Jupiter and Ganymede are barely indistinguishable from one another. So when you subtract those two numbers, you're going to lose most of the precision that the 64-bit double precision number would carry. And when we're doing this over and over and over, because we're doing numerical integration, if you do not have that right, those numbers completely throw you off. Or you're trying to target a maneuver in the order of meters per second, or say millimeters per second, when the distance and you're propagating relative. So the 64-bit number just cannot represent what you're trying to do. It cannot keep your 1 millimeter per second precision on velocity relative to the sun in something that is 30 astronomical units out. It just can't. So in our work, a lot of thought has to go into how precisely do I break this problem? I'm going to solve this part in high precision up to Mars. Then I'm going to chop it off and I'm going to solve it using another set of units from say here to there. And then I'm going to solve it in yet another set of units between there and there, so that they can represent all the numbers, so that all your numbers are approximately within the same scale. You have to minimize subtraction. You have to, multiplication is mostly okay. If you're going to add many numbers, you have to use some techniques for adding floating point that first adds numbers of similar magnitude and keeps track of the error, and etc. So it's quite a topic, floating point calculation.
Okay. So I want to get into also, well, I think mission design first, as far as designing tours of the outer planets. So a mission like Cassini and Europa Clipper, once they get to the planet, and they're usually looking at a moon. So say for Europa Clipper, it's looking at Europa. Instead of getting into orbit around Europa, it gets into orbit around the main body and then just does flybys of Europa. So can you talk a little bit about, is it a delta V constraint that you can't get into orbit of one of these small moons?
Yeah, so one, yes, it's much more, say, Europa. And another one, for the Europa case in particular, it's also a radiation issue. Jupiter has a massive radiation environment. And if you were orbiting Europa, the spacecraft would get fried in, I don't know, 3 months, 6 months, I don't know, but very quickly it would get fried. So in that case, there's a secondary constraint. In addition, when you have an orbit around the body, changes of inclination are very expensive. And if you were just orbiting Europa, you would be very nicely looking at a certain region, but it would be very hard for you to change the inclination of your orbit. Whereas if you're orbiting the planet, you can very quickly change the inclination relative to the satellite relatively easily due to the flyby of the body. So when you fly by the planet and use the satellite as a flyby, you are taking advantage of its mass to provide you delta V that you don't have to carry as fuel. Whereas if you just orbit the satellite, all the maneuvering that you want to do, it's on your own. You got to perform it with the engine because you have absolutely no source of delta V other than your thrusters. So that's one of the reasons. Injection is easier. What is called global coverage, namely looking at the whole satellite, it's enabled. And also you can have things for after the mission is over. Cassini was thought that it could be sent elsewhere after Saturn. We didn't do it, but it was possible around 2011. It was still possible to send Cassini onto the solar system, like release it from Saturn and send it elsewhere. Maybe not to inject into another planet, but to send it a la Voyager somewhere else. Mm-hmm. So imagine it would have been amazing. You orbit Saturn, you look at Titan, you look at Iapetus and Dione and all those things, and then you're done, and then you just go elsewhere and look at another planet as a flyby, and then you escape. It would have been amazing. And only because it's a probably the most versatility for outer planet satellites, solar system exploration.
So before I forget, you brought up, I think this week or last week, that you almost erased the Cassini flight software, if I remember correctly. So can you tell that story of how that almost happened?
Yeah, I think it has happened to everyone. It wasn't the flight software. It was the navigation solutions.
Okay.
It was so you receive all the telemetry, and then you have the solutions, the orbit determination, and the maneuvers that you've calculated, all the data, everything. So all that is stored into protected network called FlightOps, the flight operations computer, in building 230 inside JPL. It's a beautiful building, a historic landmark where all the deep space navigation is. We saw building 230 now with Mars 2. That building is where I used to work. So you are working and you have to manipulate a lot of data. And it happened to us, but when it happened to me, it was horrible. That in trying to move certain thing to something else, I thought I made a mistake, and I used my the up key to reissue the command, and I didn't realize that it was a recursive delete. And I just clicked it, turned around, come back, and I don't know, 3 minutes had passed or 2 minutes, I don't know. And in those 2 minutes, it completely wiped out half of the navigation. It's all work of everyone. Just know 5 weeks that alone is. I'm going to jump off a bridge if this is the case. But thankfully, obviously, Cassini knows this, so they have very strong backups. So they essentially snapshot the totality of the system every so often, and I was able to quickly retrieve it. You can quickly restore everything to a pristine state. People did lose work, like say half an hour worth of work. So there was work loss. There was a cost to this. But then they kind of throw you a party. They are like, okay, well, welcome to the team. You're an idiot like everyone else, and make sure that never happens again. And yeah, sadly, it happens to almost everyone. It's super embarrassing. I am not proud of it, but well, it happened to me too. It was very extremely mortifying.
As a welcome to the mission design team, kind of thing. So
yeah, horrible.
So I also want to ask you some questions about doing the tour design. So going back to the tour design, so you're doing orbits around Jupiter and you want to do flybys of Europa, but you use Europa kind of as your engine doing flybys to adjust the orbit around Jupiter to plan the next flyby around Europa. So can you talk a little bit about that part of mission design as far as how to, I guess first of all, I'm guessing the overarching goals is you want to get global coverage of Europa, say when you want to actually go there. So how do you set up these flybys kind of from, I guess, a numerical point of view of how to actually, the math of setting up a flyby, getting some sort of lat-long coverage as you're going down, but also setting up that pass such that the next time you come around, you'll get a different lat-long kind of view of the planet. I'm not sure if I asked that question clearly.
Yeah, that's kind of the no, I think I get it. That's kind of the secret sauce of mission design. So most moons are tidally locked to their planet, meaning that they always show the same face toward their planet and the same outward face to the planet. Like our moon, always the same faces up. It's the same story with Europa, the same with Triton, same with all of this. So that's one element. Most of them are nearly circular. And in the case of Jupiter, the moons are in resonance. Namely, the period of one is an integer multiple of the period of the others. At least the Galilean moons are in a resonant orbit. So when you're flying by, you normally encounter the satellite at the same location in that resonance, and you yourself become resonant too. So you say, I'm going to have the period of the spacecraft be an integer multiple of the period of the moon. So I guess the period of the moon, an integer multiple of the period of the spacecraft is backward. But so say I want Cassini or Europa Clipper or Neptune Odyssey or any of these. I wanted to orbit once as orbits in the previous time I flew by it. And due to all these characteristics of being circular, of having tidally locked system, and you're encountering at the same place, some things ought to change. So you are gonna, everything is going to be identical. The phase where you're flying, the lat long where you're flying of your closest approach, the time where you will be flying, after the 4 period. So the only thing that changes is your inclination. And then as you start changing the inclination, that little point, the spacecraft point, starts climbing a little bit along the longitude line. And then you reach a point where you have to do it backwards. So then it starts walking downward. And then at some point you cover that face of the satellite. And then you create another kind of flyby, which is no longer resonant. It's called non-resonant, or pi. So it's 2 separate ones. The non-resonant is one kind of flyby, and the pi is another kind of flyby. So you change to another side of Europa, and then you perform it again. So in the case of Europa Clipper, we have 4 such regions to look at 1/4 of a hemisphere, half of a hemisphere, another half of a hemisphere, another half of a hemisphere, and another half of a hemisphere. So 4 quarters by changing then a collection of non-resonants, then resonant transfers again, then a pi transfer, then a collection of non-resonants, and then resonance again. And then we cover the totality of the hemisphere in 4 different periods of the mission. And those are the 3 main kinds of transfer. And the reason why we can do it, both at the same time do observation and staging the next flyby, is because all these properties of being tidally locked, being nearly circular, nearly equatorial in this case, and having our transfer be our main tool, be an integer multiple of the satellite orbit. That's how you can set up all the flybys.
Okay. Okay, that's super interesting. So is that a bit of, so how do you solve for calculating those flybys? Is that a bit of a shooting method as far as how to actually solve for those?
First, patch conic with all these matching B infinity, and there's another way to. You don't have to match B infinity when you are doing resonant transfers. Only when you're doing non-resonant. But it's the same argument of only getting the outbound B infinity that corresponds to a given inbound B infinity. Just couple maybe 3, maybe 4 flyby in patch conic or collocation or something like that. Then you get to say flyby is down. Then you do another patch conic, and then you solve the whole thing again, and the whole thing again. It's always done step by step.
Okay.
Like chunk by chunk.
Okay. And I also want to get into the navigation side of things, because I feel like that's a whole another different type of math problems to solve. So the first part of it, I want to, so can you talk a little bit about how deep space orbit determination works, say for a Cassini spacecraft?
Yeah, so Cassini has had, rest in peace, and antennas that talk to antennas that we have on Earth, the Deep Space Network, also managed by JPL. Antennas in 3 locations on Earth, separated by approximately 120 degrees longitude to scan the whole planet. So Goldstone, California, Madrid, Spain, and Canberra, Australia. So Cassini sends a signal, and the Deep Space Network measures the range and range rate, or it gets the Doppler of that distance. So the only thing you're trying to get is the kind of where you are and how quickly are you approaching or departing. With those measurements, you also have and then you see signal, and then you say, okay, if I am this kind of Doppler shift, but I saw this other kind of Doppler shift, what does that mean? That means that I'm not where I thought I was. I am a little bit to the left, a little bit to the right, a little bit faster, a little bit slower. So orbit determination, and now solve the inverse problem of simulation, is given the data, I want you to give me the initial conditions and the orbital and the overall trajectory where you were. And there's also optical navigation, where you take a picture with the spacecraft and you put, for example, the planet, a moon, and the stars behind it. And you take a picture and you send it to Earth. And then you're like, okay, at this time, looking in this orientation, this is what I saw. So where am I? And then you have to simulate everything, simulation of the stars, the stellar aberration of the stars, and say, okay, I should have seen that star a little bit more to the left if I were where I thought I was. So I'm not. How should I move so that I see what I'm seeing in the picture? So that's called optical navigation. And I mean, you have many other kinds of navigation, but in general, that's the point, to receive data and use that data to tell you where you are. And it is the inverse problem, and a super massively complex topic, but that's the gist of it. We use antennas, we use pictures. If you were on Earth, you would use GPS, but obviously there's no GPS outside of Earth. And yeah, so you just use that, find out where you are compared to where you want it to be. And because inevitably you are not where you want it to be, even by a little bit, then you schedule a maneuver, you send it to the spacecraft, executes a maneuver, and puts it back where it should be. And that's the life cycle of flight path control.
So as far as getting the range and range rate from a deep space network, is the accuracy of that dependent on the accuracy of how you know the declination and azimuth of where these antennas are pointing? Kind of a very fine precision of, I know where these antennas are pointing, as far as sending and receiving the signal. So is that part of what
yeah,
yeah, go ahead.
Yeah, I mean, the antennas, we know even how the plate tectonics move underneath them. We know precisely where they are, everything about them. We know the weather, the exact orientation, the atmospheric effects that are subject to them. We know everything about those antennas, and we know everything about Earth that we can know. The precise orientation of the Earth, day by day, we get different data to know all of that. Yeah, this is extremely intricately accurate work. A difference of a few centimeters in the antennas, like if there was an earthquake, the Deep Space Network would notice if it moved its antennas.
Okay. And then one thing I want to get into as well, as far as orbit determination, is that, say you're doing optical navigation and the spacecraft sends back a picture. So then you can say, okay, given what I see, I can tell you where you are, but that's at a given time. And then when you want to send that data back, that says you were here at this specific time. So I want to go into the kind of the relativity corrections, the aberration corrections, because I think they're really interesting. And there's one that I don't understand, because the first few that I've seen the SPICE documentation that are, the light time that it takes to travel for the photon from the spacecraft down to Earth, or the radio signal, and the same thing going back. But then there's another correction, if I remember correctly, when I was reading the SPICE documentation, that has to do with the correction due to the acceleration of the observer and the target with respect to the solar system Berry Center. I don't know if that sounds right or not, but can you talk about the kind of the aberration corrections that go into that orbit determination?
Yeah, of course. So the non-aberration is very simple. The light has a finite speed, and the way you see the sun is not where the sun is where the sun was. And when you get the geometric position, it would tell you where the sun is, but what you are looking at is where the sun was. And that 8-minute light delay between the Earth and the sun, if you wanted to see how are you looking at the sun from Earth, you would need to compute its geometric position 8 minutes ago. That one is relatively easy to understand. And the aberration is just something that is due to your own motion. When you're measuring velocities, this matters for velocity. If you are running, if you're standing in the rain, that's always example that is clear, then the rain looks as if it's coming, and it's raining horizontally, like vertically, I'm sorry. You would look at the rain falling like this. But if you were running into the rain, all of a sudden it would seem as if there is a slope to the rain and its velocity would be different. So you would say like, oh, the rain is vertical. And then someone would tell you, no, the rain is slanted. And you would say like, but how can that be? I saw it vertical and you see it slanted. And you're like, oh, it's because of my velocity. I'm running into the rain. It's not the rain that is different. That is the aberration correction. Because you are moving. So the Earth itself is moving. It depends on who's talking, right? Because it depends from where to where you are doing. But if you are on Earth, Earth itself is moving. And in moving, it's modifying how it looks at the star. And if you're looking at a star, then the star itself is also moving. And depending where you're looking at, it can add this extra velocity component. That is the aberration. It's not an artifact, but it's a relativistic effect, not from the Einstein theory of relativity, but from the more Galilean relativistic. Like there's motion. So you have this addition of velocity.
Okay, so going off of kind of how the stars are moving, I want to ask you a bit about reference frames. So say the EME 2000 frame and how it's, I guess, possible to define an inertial reference frame with respect to the stars when the stars themselves are moving.
So you can't. It's impossible to have an inertial reference frame. That's just, but it's almost philosophical. In practice, you define inertial reference frames precisely by pinning it down to distant quasars. So that is how EME 2000 is defined, which is really called ICRF 2000. We call it EME 2000 or J2000. So because the quasars are extremely distant, extremely super, I mean, I'm talking billions of light years away, for all practical purposes, in our terms, they can be considered fixed. They are moving, sure, but they are so grossly far away that we cannot make out that motion. And we just use several of them to pin down a certain orientation in space. And again, you just fix it to quasars. And you're like, okay, that quasar over there, that one over there. I forget how many. I think it's 50 something. And they update ICRF every time. I forget what version they are on now. And you use that to define what you mean by inertial fixed unaccelerated. But again, in reality, such thing doesn't exist. I mean, the universe is expanding, just in that there's no inertial frame that we could ever hope to pin down, because everything is moving. Since the Big Bang, the universe is expanding. We could not just say there's this thing that is not moving. But again, that is touching into relativity, which is, again, fascinating, important. We use it, mechanics.
Mm-hmm. Okay, so I want to also get into SPICE. So can you talk a little bit about kind of what SPICE is, the whole SPICE system and SPICE kernels?
Yeah, it's a computational system for scheduling observations. Originally, that's why it was done, because the mission designers at JPL had their own tools and they knew how to do their things. And they were very happy with their crazy science. But when you gave the study, they also are super smart people, but they are not rocket scientists, right? They are planetary scientists. And so it was a huge problem that they didn't know how to, for example, see how the planet would look from the vantage point of the spacecraft. And then, I mean, it's not fair to ask them to also get a PhD in astrology so that they can do their planetary science. So that's where SPICE comes in. The JPL paid for this wonderful project, and they have to this day a wonderful team of people to make this suite of software tools that will be very easy to use, precisely to schedule observations and interpolate ephemeris, essentially to manipulate all the solar system geometry in a way suitable for scheduling and planning scientific observations. And so you can do many things. The most famous one for us is ephemeris interpolation, but it also does frame transformation, time system conversion. It does. It finds events. It can define different shapes of the things. It can find eclipses. It's just a wonderful little toolkit. It's originally written in Fortran. If you ever want to see good Fortran, you have to look at SPICE's source code. It's the best Fortran source code I have ever seen in my life, and there's nothing like it. It's the only Fortran that I like. Everything else makes me throw up.
Wait, so what version of Fortran was that written in? Is it pretty modern Fortran? And wait, does it have go-to
77.
statements?
No, Fortran 77.
Oh, okay.
Absolutely.
Okay.
It's nasty, but it's beautifully written. It's beautifully documented. It has go-tos. It has even worse than go-tos. It has what is called the variant return statements and the variant entry position. You don't enter a function and exit a function at the same point. You can enter at arbitrary points and exit at arbitrary points. It's crazy. Very difficult to follow. But again, their Fortran is the only Fortran worthy name that I have seen. I know the one that we use, SPICE, is an automatic, because it makes it easy to link the libraries. Also the same software version, which is not written by humans. It's a computer translation of Fortran 77 to C.
Okay. I didn't know that. So going into kind of more software engineering, could you go over some kind of fundamental differences between a C and C++ and a Fortran, and then in what cases it is better to use one over another?
Yeah, I think at this point they are the same thing after you have written it. After you have written the code and it's good code, they use underneath the same tool chain. So the compiler doesn't care. But the compiler does. The computer doesn't care. Once it's been compiled, what the three have in common is they generate machine instructions that is compiled into an executable that is run on the chip. The chip doesn't care if it's C or Fortran or C++. Now the programmer cares, and because you need to be efficient and fast. And in that sense, being the 21st century and being 2021, I honestly think that the only game in town is C++. C is what C++ is a better C. Is not an extension of C. C++ is what C should have become and C should have stopped being. So C++ is the evolution of C. Obviously, this is not officially the case. C and C++ are two separate programming languages. Both of them are standardized by the ISO or standard organization. They were created by different people and what have you. But C++ was the response of Bjarne Stroustrup to C. And it's a better language. And it's also a better language than Fortran for general purpose programming. When you want to only program a matrix inversion, for example, numerical C for that kind of mathematical calculation, I can see what they would use it. But as soon as you have to do any single thing else that is not just precisely, as soon as it's anything more than that, is to do connect to a network. You cannot serialize with JSON. And of course, people can say, oh, use this library, use that library. But it has so little facilities for anything else that is not a strict numerical computing that a good high quality software is no longer written in Fortran, save few exceptions. Obviously, there's always a good exception. But in general, I think people should stick to C++ and know it's no slower than C or Fortran. It's as fast or even faster. because it makes no sense. It cannot be slower. Like, why would it be slower? A computer only knows one way to multiply numbers. If you just say A times B, it's the same instruction for the processor. Doesn't matter who wrote it.
Okay. And as far as I want to get into just a little bit of kind of operating systems. So as far as, say, the differences between a Unix operating system and an OS X and a Windows. So can you talk about kind of the fundamental differences between the different operating systems?
Yeah, I mean, they are all very similar from the perspective that they are all what I call monolithic kernels. Like, they are a huge thing that has a protected space, and then the users run on top of it. The difference is that Windows is not a Unix operating system, whereas Linux and OS X are Unixes. They are different. Mac OS is not Linux, but is Unix. It's a Unix based on BSD, which is another version of Unix. And Linux is another version of Unix based on is Minix, which was a teaching operating system, improved by a kid called Linus Torvalds that eventually became the adult Linus Torvalds that we all know and love to hate. But they are all the same. So Unix is a philosophy rather than a technology. It's I mean, it's obviously there's a specification of what Unix is, but these systems have a philosophy of everything very simple. It's hard to define it, but it's everything very simple, and the user is an expert. That's the philosophy of Unix in general. You know what doing to RAM ref star, just I feel that it's something like editing a Word document, but it becomes very difficult to be an expert in Windows, to manipulate the computer like you want. So I use Windows only because some of my clients ask me to use Windows, but my workhorses have always been.
So one thing that I'm kind of curious to hear more about is how you got
absolutely shoot.
So you got your PhD at Carnegie Mellon, specializing in numerical optimization for spacecraft trajectories, but it was through the chemical engineering department. So
yeah.
Can you talk a little bit about that story and kind of how you kind of managed to find your way into there in Carnegie Mellon?
Sure, it's very simple, really. Is because I was born in Mexico, and Mexico has no aerospace. I went to college in Carnegie Mellon, who is an expert in the department, which was my knowledge. So I could reasonably expect to be accepted to that school. Whereas if my other option was applying to MIT, to Aero Astro, but I'm afraid I would never have gotten in. I didn't try. Maybe I should have tried, but I didn't try, and I didn't want to screw it up. So I went to the Mexican government, asked money for a scholarship. They gave me a scholarship, and they told me the money is yours if you are accepted. But if you're not accepted, that's it, one chance. So I just went to the best and I'll go with this guy, Larry Bigler, who is the best in the world at dynamic optimization. So, and my shenanigans worked because I came in, I thankfully got accepted. And when I came to him, I'm like, hey, I want to do spacecraft stuff. Like, he's like, well, we cannot do a spacecraft stuff. I said, oh, but I have an do whatever you want. So I'm very lucky. And that's why I went and learned literally from the best guy what I do. And I mean, it would have been fun to study aerospace, but I'm happy having studied chemical engineering. All the astrodynamics that I know, I learned by myself. So, and no complaints so far.
All right, so that's it for this episode. And hopefully you saw kind of how much math goes into mission design, because that's something that I was pretty surprised by when I started doing this job and getting a very specialized field of mission design and how everything is math. So I was actually pretty surprised by that and never really put enough thought or imagined that I would actually kind of just be doing math every single day in my job, which is pretty interesting and a pretty exciting thing to do. So some things that we didn't get to in this podcast that I would like to do if we do another episode. So as far as the SPICE system, when doing ephemeris interpolation, so basically when you have a SPICE kernel and you want to get ephemeris data from that using Chebyshev polynomials, and then why you want to use that over, say, Lagrange polynomials. I also want to get into more software engineering because we only got to it a little bit towards the end. And then off of that, just a bit more about computer clusters, because obviously the work that we do for mission design just demands a lot of computing power. I also didn't really get to the flight path control part of navigation, which I think is pretty interesting. And then more details of kind of the center switching methods and numerical considerations when doing these flyby trajectories, and say when you want to switch from a heliocentric elliptical orbit to then do a flyby around Jupiter and then back out, that center switching can have some numerical considerations. And also measuring time, because I only briefly mentioned it, but I think time is very interesting and it's very important when doing the navigation and deep space orbit determination, especially with the relativity corrections. So I think that's pretty interesting and something that I like to get more into the future. So that's pretty much it for this podcast. If you like it, please share it with anyone that you think would also be interested in it. That's probably the best way to support the podcast at this time. And thank you for watching. And if you don't already know, I have a bunch of educational YouTube videos that cover kind of similar stuff to this, so orbital mechanics type of things, where I go into the software and how to actually apply them into Python. So yeah, that's it. Let me know any questions or comments in the YouTube video, and thank you for listening to this podcast.